Welcome to Science for Sleepy, the corner of YouTube where you can lie back, close your eyes, and let the steady tide of science carry you towards sleep. Tonight, we are venturing into one of the most terrifying, and at the same time, most fascinating, ticking clocks beneath our feet, the Yellowstone supervolcano. What if it erupted? What would that mean for you, for me, and for the billions of people who would have to face its shadow? Let's settle in, because this is a story that begins with ash, silence, and numbers so large they almost slip past the imagination. Let me start with something startling. If Yellowstone were to release its full power in a single catastrophic eruption, the amount of material it could eject into the atmosphere might be measured in hundreds of cubic miles of rock, ash, and gas. Imagine, for a moment, a hole in the earth large enough to swallow an entire city, filled not with buildings or streets, but with pulverized stone rising upward into the sky. And that ash wouldn't just settle neatly around Yellowstone itself. Winds could carry it across the entire continent, dusting cars in New York, dimming skies in Florida, and choking fields in Kansas. In some places, the ash might be only a thin layer, the way a fine snowfall covers a driveway in winter. But in others, it could be thick enough to collapse rooftops and render highways impassable. And all of this could happen in less than a week. Before we go further, I'd love it if you could take a moment, while you're drifting here with me, to head down to the comments and tell me where you are listening from. Is it evening where you are, or is it the middle of the night? Sometimes I imagine people listening to these videos from dorm rooms, from city apartments, or even while camping out under the stars. It's a fun thought to picture all of us connected by this strange conversation about the sleeping giant beneath Wyoming. And, since we're talking about eruptions, here's a polite but slightly explosive reminder. If you haven't already, subscribe to Science for Sleepy. Think of it like this: if Yellowstone erupted, you wouldn't want to be caught off guard, right? Subscribing here is like keeping your own little early warning system for science videos. And we upload every single day, so if you come back tomorrow, you'll find another story waiting for you. Now, let's walk slowly into this idea of a supervolcano, because the phrase itself already sounds exaggerated. When you think of a volcano, maybe you picture Mount St. Helens or Mount Vesuvius, something with a sharp peak, a cone, and fiery lava sliding down the sides. Yellowstone is nothing like that. It is in fact the opposite. Flat, forested, calm, a wide plateau covered with pine trees, bison, and tourists snapping photos near geysers. But beneath that postcard scenery lies one of the largest magma reservoirs in the world. It is not a neat cone, it is a vast, irregular chamber, more like a pot of soup left simmering on a stove. The problem is that the pot is deep, and the lid is the crust of the earth itself. Every once in a very long while, that lid blows. What's particularly unnerving is that Yellowstone has done this before at least 3 times in the past 2 million years. Each of those eruptions was thousands of times larger than what Mount St. Helens produced in 1980. Scientists classify them as super eruptions, the kind that can alter climates for decades. And if history teaches us anything, it is that what has happened before could, in theory, happen again. But let's pause and strip away the drama, because this is not about fiery explosions like in movies. Most of the danger of Yellowstone comes not from lava but from ash. Think about a single handful of fine volcanic ash, the kind that looks like dust but feels gritty between your fingers. Now multiply that by trillions of handfuls drifting across the skies. It would turn the air opaque, like fog made of stone. It would grind engines to a halt, clog rivers, and blanket farmland. Even a few millimeters of this material on a wheat field could stunt the crop. And even a thin layer on an airport runway would ground planes indefinitely. The boring truth of Yellowstone is that the catastrophe lies not in rivers of fire but in layers of suffocating dust. If you stand today in Yellowstone and look at the bubbling pools, the steaming geysers, the ground trembling just enough to remind you that something is alive below, it can be hard to imagine that such calm beauty could someday turn into a global event. Yet that duality, the peace above and the turmoil below, is what makes this topic worth studying. And while the probability of a super eruption happening in our lifetime is very low, the consequences are so vast that scientists keep a watchful eye. They track every tremor, every chemical change in the hot springs, every bulge in the ground, because when the Earth speaks, it doesn't always whisper politely. Sometimes it clears its throat in a way that shakes continents. The interesting part is that Yellowstone doesn't have to erupt fully to cause trouble. Even smaller eruptions, the kind that don't make international headlines, could still disrupt air travel, scatter ash over farms, or change local ecosystems. Imagine driving through Wyoming and seeing a sudden plume rising like a thundercloud, ash falling like grey snowflakes on your windshield. That scenario is far more likely than the apocalyptic vision, but even so, it would be enough to remind us that we are living above one of the most unusual pieces of geology on the planet. And here is a small detail that often gets overlooked. The last time Yellowstone erupted on a smaller scale, it left behind a lava flow so massive that it still defines parts of the landscape today. You can hike over those rocks, camp beside them, and never fully grasp that you are standing on frozen rivers of once molten earth. There is a kind of quiet lesson in that, isn't there? That something so dull and still can be the echo of a force powerful enough to rewrite climates and redraw maps. The question, of course, is not just what would happen if Yellowstone erupted, but what it would mean for you, sitting wherever you are right now. Would your skies darken? Would your grocery store shelves empty? Would your internet connection go silent? Or would it pass you by as another headline, distant and strange, while life carried on? These are the kinds of questions that remind us how tightly woven the fabric of the world really is. One tremor beneath Wyoming could tug at threads across the globe. So let me ask you this as we close this first step into the story. When you hear about Yellowstone, do you feel fear or do you feel awe? Is it more terrifying to know that the ground beneath a national park hides such power, or more humbling to realize that, despite all our technology, we remain vulnerable to the slow, indifferent clock of geology? If Yellowstone were to stir from its long silence, the first signs would not be explosions or roaring fire. They would be quiet, ordinary, almost boring details that most people wouldn't notice until scientists explained them. That is the unsettling truth about volcanic awakenings. They whisper long before they scream. And if you were walking through Yellowstone on such a day, perhaps on a family trip, you might see hints of that whisper without realizing their weight. Imagine standing at Old Faithful, waiting for the geyser to erupt like it always does, clockwork and predictable. But today, the timing is off. Instead of spouting after 90 minutes, it takes 100, or perhaps 70. The water sputters, shoots lower than expected, or roars higher than usual. Tourists might laugh and shrug, thinking nature doesn't follow a schedule. But to geologists, that irregularity is like a doctor noticing an irregular heartbeat. It isn't a guarantee of disaster, but it is a symptom worth writing down. The ground itself would also offer subtle warnings. Yellowstone is not a static park. The surface there is always rising and sinking, breathing slowly as magma shifts below. Usually, those movements are measured in millimeters each year, so slow you'd never feel them. But if the supervolcano began to prepare for an eruption, the earth might bulge upward by inches or even feet, like bread dough swelling in an oven. Roads might warp ever so slightly, parking lots might crack, and boardwalks near hot springs might tilt at odd angles. If you were driving across the park, you might just think the asphalt was poorly maintained, never guessing you were literally rolling over a growing dome of earth. Then there are earthquakes. Yellowstone is already one of the most seismically active regions in the United States. Hundreds, sometimes thousands, of small quakes ripple through it each year. Most are so weak they cannot be felt without instruments. But in a period of unrest, those quakes could come in swarms, dozens in a single day, with some strong enough to rattle dishes in cabins or knock a framed picture off the wall in a hotel near the park. To you, as a visitor, it might just feel like an odd nuisance. But to volcanologists, earthquake swarms are like an alarm clock ringing faintly in the distance, reminding them that magma is on the move. Now, if you've ever smelled rotten eggs near Yellowstone's hot pools, you know that the earth releases gases from deep below. sulfur dioxide, carbon dioxide, and other compounds seep through the ground all the time. Most of the time, they rise in harmless amounts, blending into the steam that makes the park so iconic. But if Yellowstone were awakening, those gases might spike, releasing in higher concentrations. Animals grazing nearby could collapse, suffocated silently by invisible clouds pooling in low valleys. Scientists would measure those gases and note changes: more carbon dioxide here, more sulfur there, like detectives following a trail of clues. And yet, none of these signs would necessarily mean the end was certain. Volcanoes are notorious for their false alarms. Mount St. Helens rumbled for months before 1980, and even then, people weren't sure what it would do. In Iceland, eruptions sometimes simmer for weeks before subsiding back into dormancy. Yellowstone, with its immense size, could easily stir without actually exploding. The Earth, after all, is under no obligation to follow human timelines. If the signs did continue, though, scientists at the Yellowstone Volcano Observatory would be among the first to notice. Their job is not to panic the public, but to measure, catalogue, and compare. They'd release quiet bulletins online, technical notes about seismic activity, gas emissions, and ground deformation. For most people, those updates would pass unnoticed, buried beneath headlines about politics or celebrity news. But for those who do pay attention, each bulletin would feel like watching a needle slowly rising on a pressure gauge. Picture yourself reading one of those bulletins late at night. The language would sound calm, even boring. Earthquake swarm recorded in the Norris Geyser Basin, with over 1,000 events measured. A single sentence like that might not feel like much, but behind it is the weight of something vast. 1,000 little heartbeats of the Earth, each too small to feel, but together hinting at restlessness. Would you shrug it off, or would you start to wonder if this is the beginning of something history will remember? Of course, you might ask, what about the animals? They too are often mentioned in stories of natural disasters. Birds abandoning forests before wildfires, dogs barking before earthquakes. In Yellowstone, perhaps herds of bison would shift strangely, moving away from familiar grazing spots. Maybe elk would cluster near rivers, restless and unsettled. To a casual hiker, it might look like nothing more than wildlife behaving unpredictably. But to rangers who spend years watching these animals, any odd migration would stand out. And there's another curious detail about volcanic unrest: the color of water. In certain hot springs and pools, chemical changes underground can alter the minerals dissolved in the water, shifting colors in ways that tourists might even find pretty. A deep blue spring might fade into green, or a yellow hue might become more intense. People would take photos, post them online, and marvel at how beautiful Yellowstone looks this summer. But beneath that, beauty could be chemical fingerprints of magma pushing closer to the surface. The first signs, then, are not apocalyptic. They are quiet, scattered, often invisible until you know how to look. They would creep into daily life like background noise, growing louder until it became hard to ignore. And that slowness is part of what makes Yellowstone both fascinating and frightening. Unlike an earthquake that strikes in seconds, or a hurricane that can be tracked on radar, a supervolcano's awakening could stretch across months, maybe years. A kind of slow-motion tension, where every day might feel like the last calm before the storm, even if the storm never comes. Imagine, then, the psychological weight on those living nearby. Farmers in Montana waking to tremors that rattle their barns. Schoolchildren in Wyoming practicing earthquake drills, not knowing if the shaking under their desks is the usual or a warning. Families in Idaho checking news bulletins about ash preparedness kits, wondering if they should stock up on masks and bottled water. Life would not stop, but in the back of every mind would be the whisper, what if this is it? It's worth noting that Yellowstone has teased humanity before. In 1959, an earthquake struck near the park, killing dozens of campers and triggering a massive landslide that dammed a river. For a moment, people wondered if the eruption had begun. It hadn't, of course, but the fear was real enough to leave a mark in memory. a reminder that this landscape is alive in ways most places are not. So the first signs of Yellowstone awakening would not be a single dramatic event. They would be a series of small, easily overlooked details: a geyser off schedule, a road that cracks, a cluster of quakes, a bison herd moving oddly, a color shift in a spring, gas levels creeping higher. Each on its own could be dismissed. Together, they would form a picture, a warning painted not in bright strokes but in quiet smudges. The unsettling part is that we might not know whether those signs are the beginning of a world-changing eruption or just another restless stretch in Yellowstone's long life. And that is perhaps the hardest part for humans to accept, that sometimes the Earth speaks in riddles, and our job is not to solve them instantly, but to live with their uncertainty. So let me leave you with this thought for now. If you were standing on the boardwalk in Yellowstone, feeling the heat rising from a spring, and you saw the ground tremble ever so slightly beneath your feet, would you see it as a thrilling brush with geology, or would you see it as the first domino in a chain too large to stop? When you hear the word volcano, your mind probably sketches a certain picture: a tall mountain, maybe snow-capped at the peak, with smoke curling out of a crater. You might think of Vesuvius looming over Pompeii, or Mount Fuji rising in Japan, or Mount St. Helens before its famous collapse. But Yellowstone doesn't look like any of those. If you were standing in the middle of the park right now, you would not see a cone-shaped peak, or even a single crater. You'd see flat valleys, pine forests, rivers, and herds of bison grazing calmly. And that is exactly what makes Yellowstone both unique and deceptive. Its volcanic identity is hidden beneath beauty. The word supervolcano sounds like something invented for a science fiction novel, but it is, in fact, a scientific classification. A supervolcano is not defined by height, or lava fountains, or how terrifying it looks. It is defined by the scale of its eruptions. Specifically, a supervolcano is any volcano that can erupt with a volume of at least 240 cubic miles of material. That is a number so large that it's nearly meaningless on its own. So let's shrink it into something more familiar. Imagine you have a standard dump truck, the kind you see at construction sites. Now imagine filling that truck with volcanic ash and rock. You'd need billions of trucks lined bumper to bumper across continents to equal what a super eruption can release in a single outburst. Yellowstone has done this not once, not twice, but 3 times in the past 2 million years. Each time, the eruption was large enough to carve out massive calderas, depressions so vast that you cannot see their edges in a single glance. These calderas are not sharp-walled craters like on postcards from Hawaii. They are more like enormous bowls, miles wide, where the land sank after the eruption emptied the chamber beneath. Today, many of Yellowstone's most famous geysers and hot springs sit inside those bowls, quietly steaming above the scars of past explosions. But what makes Yellowstone different from ordinary volcanoes is not just its size. It is the system beneath. Most volcanoes are fueled by relatively small pockets of magma that rise toward the surface. Yellowstone's magma chamber, by contrast, is a sprawling reservoir that extends for tens of miles, stretching beneath much of the park and beyond. Imagine a blister under the skin of the continent, filled with molten rock, gases, and heat. It is not a neat chamber, but a tangled network of partially molten material. Scientists use seismic waves, ripples from earthquakes, to map its shape, the way a doctor might use ultrasound to peer inside a body. What they see is both astonishing and humbling, a system so large that it challenges our sense of scale. Now, you might be wondering, why is it even there? Why Yellowstone? The answer lies in a geologic feature called a hotspot. A hotspot is a place where heat, from deep within the mantle, the layer beneath the Earth's crust, rises up like a slow, invisible fountain. Most volcanoes form near tectonic plate boundaries, where plates collide or pull apart. Yellowstone, however, sits in the middle of a plate. The hotspot below it burns steadily upward, melting rock into magma. Over millions of years, as the North American plate drifted slowly westward, the hotspot stayed in place. The result is a trail of ancient volcanic scars stretching across Idaho, marking where the hotspot once pierced the crust before finally resting under what we now call Yellowstone. It's fascinating, isn't it, that the ground beneath your feet could carry such a long memory. If you were to fly over the Snake River Plain in Idaho, you could trace that volcanic trail like a series of breadcrumbs, each marking an eruption older than the last. Yellowstone is simply the latest stop in that chain, the current outlet for heat that has been simmering beneath the continent for millions of years. But here's something worth slowing down on. The word super in supervolcano does not mean most likely to erupt or constantly dangerous. It is a description of potential, not schedule. Yellowstone has erupted on a massive scale 3 times, yes, but the last of those was more than 600,000 years ago. Statistically, it does not appear overdue, despite what sensational headlines sometimes suggest. In fact, the odds of a super eruption happening in your lifetime, or even in the next 1,000 years, are extremely low. Scientists stress this again and again. Yellowstone is restless, but that does not mean it is ready to explode. Still, the classification matters because of what it tells us about possibility. A volcano like Mount St. Helens can devastate a region. A supervolcano like Yellowstone could alter the planet. It is a reminder that the Earth holds power far beyond the scale of human engineering or planning. For all our satellites, for all our sensors, we are still fragile creatures living on the thin crust of a planet that occasionally flexes its muscles. When you hear magma chamber, you might imagine it as a huge cavern filled with bubbling lava, glowing orange like something out of a movie. In reality, it is more complex. Much of the chamber is not fully molten, but a mix of solid crystals suspended in partially melted rock. It is not like a swimming pool of lava. It is more like a sponge soaked with heat, with pockets of liquid rock scattered throughout. Only when enough pressure builds and enough gases accumulate can that mixture surge upward in a catastrophic release. That complexity is what makes predicting eruptions so difficult. If Yellowstone does erupt again someday, it may not be a super eruption. It could just as easily be a small lava flow, the kind that might disrupt part of the park but not the planet. In fact, smaller eruptions are far more likely. But the very fact that the system is capable of something so immense places it in a rare category, one of only a handful of known supervolcanoes on Earth. Others exist in Indonesia, New Zealand, and South America. Each of them is a sleeping reminder that our planet is not a steady stage, but a living, shifting body. Let me give you a comparison that might help fix the scale in your mind. The eruption of Mount Tambora in 1815 in Indonesia was the largest eruption in recorded human history. It released about 10 cubic miles of material into the atmosphere and caused what became known as the year without a summer. Crops failed across Europe and North America. Snow fell in June in New England. Thousands starved as harvests collapsed. That was 10 cubic miles. Yellowstone, in a super eruption, could release more than 20 times that amount. 20 times the ash, 20 times the gas, 20 times the disruption. And yet, if you stood in the park today, all you would hear is the soft hiss of steam vents and the low calls of bison. There's something quietly humbling in that, isn't there? That the most powerful volcano on the continent does not loom above you as a cone but lies hidden, almost invisible, under grasslands and forests. That its danger is measured not in fiery rivers of lava but in the slow, suffocating spread of ash. That its history is written not in dramatic peaks but in subtle depressions across a landscape where families picnic and children toss pebbles into streams. So when we call Yellowstone a supervolcano, what we really mean is that it belongs to a category of geologic features that are both rare and capable of reshaping global systems. It is not about constant threat, it is about capacity. And understanding that capacity helps us see our place on Earth more clearly. We are not masters of the planet, not architects of its deepest processes. We are simply tenants, fortunate to live during one of its quieter chapters. And here's the question I'll leave you with tonight. When you think of Yellowstone as a supervolcano, not as a park with geysers and elk, But as a scar of past eruptions and a reservoir of potential future ones, does it change the way you imagine the ground beneath your feet? Do you feel comfort in knowing that it is unlikely to erupt soon, or unease in knowing that the possibility is written into the very bedrock of the continent? To understand what Yellowstone might do in the future, you have to step back and look at what it has already done. The Earth, after all, has a way of keeping its own records. Not in books or libraries, but in rocks, ash layers, and scars carved into landscapes. Yellowstone's history of eruptions is written in stone, and when scientists read that story, it is both fascinating and sobering. The park has erupted on a massive scale at least 3 times in the past 2 million years. Each one of those eruptions was so immense that calling them explosions feels almost too small. They were closer to planetary events, eruptions that reshaped climates, altered ecosystems, and left permanent marks on the face of North America. The oldest of the 3 occurred about 2.1 million years ago. To put that into perspective, humans as we know them did not even exist yet. Our ancestors were scattered across Africa, still shaping primitive tools from stone. While they chipped flint, Yellowstone tore open the crust of the earth and released more than 2,000 cubic miles of material. Try to picture that. Imagine taking every single mountain in the Rockies and grinding them into dust, then hurling that dust across the continent. That's the scale we're talking about. The eruption left behind what geologists call the Huckleberry Ridge Tuff, a layer of hardened volcanic ash that can still be found stretched across parts of the western United States. The caldera from this event was nearly 60 miles long, a scar so large that, if you were standing in it, you would not see its edges. You would simply feel as if you were in an unusually broad valley. The second massive eruption happened about 1.3 million years ago. By then, early humans had begun to spread beyond Africa, but they would never have witnessed Yellowstone itself. This eruption, though smaller than the first, was still massive by any normal standard. It released about 370 cubic miles of material, leaving behind what is known as the Henry's Fork caldera in Idaho. If you visit that area today, you can drive across it without realizing what it is. The land looks like rolling hills, farmland, and rivers. But beneath those quiet scenes lies the memory of an eruption that would have darkened skies across much of the world. The most recent of the 3 great eruptions happened about 630,000 years ago. By then, our human ancestors were a little closer to the people we are today. They used fire, built shelters, and hunted in groups. Somewhere across the globe, bands of early humans may have looked up at skies darkened by Yellowstone's ash without understanding what they were seeing. This eruption released about 1,000 cubic miles of material and created the Yellowstone caldera that now defines the park. If you've ever stood at Yellowstone Lake or gazed across Hayden Valley, you've been looking at the sunken floor of that ancient eruption. The lake itself is partially a product of the caldera's collapse. In other words, when you admire the beauty of Yellowstone today, you are standing in the aftermath of one of the greatest natural disasters the planet has ever seen. It is worth pausing here to think about what those numbers mean. Mount St. Helens in 1980 released about 1 cubic mile of material. 1. People watched in awe as the mountainside collapsed and a massive plume shot into the sky. Whole forests were leveled, rivers were choked with mud, and ash fell as far away as the Midwest. That was 1 cubic mile. Yellowstone's smallest great eruption was hundreds of times bigger. Its largest was more than 2,000 times bigger. Trying to hold those scales in your mind is like trying to imagine the distance to the stars too large to truly grasp, yet somehow real. These 3 eruptions are the ones that capture the imagination, but they are not the whole story. Yellowstone has also erupted dozens of smaller times in between. These smaller eruptions produced lava flows, some of them vast enough to cover entire valleys. One flow, called the Pitchstone Plateau, erupted about 70,000 years ago. If you hike there today, you can walk across the black rock of that lava field, cooled and hardened, its surface now dotted with trees and wildflowers. It is quiet now, but once it was a river of molten rock spreading across miles of land. And then there are the hydrothermal explosions. These are not super eruptions, but they are dramatic in their own right. Sometimes, when water trapped underground becomes superheated, it can burst forth violently, creating craters and blasting rock high into the air. In Yellowstone's past, some of these hydrothermal blasts have created craters hundreds of feet wide. Imagine standing near a hot spring one day and, without warning, hearing the earth roar as steam and rock exploded skyward. Those events remind us that Yellowstone's power is not only in its magma, but also in its boiling water systems, which can behave unpredictably. When scientists study Yellowstone's past eruptions, they look not only at the rocks but also at the ash. Layers of volcanic ash can be traced across the continent, found in soil and sediment as far away as the Gulf of Mexico. These layers serve as timestamps, linking the Yellowstone eruptions to climate changes recorded in ice cores and ocean sediments. After the last great eruption, the planet cooled noticeably. Sunlight was blocked by ash and sulfur aerosols in the atmosphere. Crops withered, animals died, ecosystems shifted. It was not the end of life, but it was a significant disruption. You might think, if Yellowstone erupted 3 times in the past 2 million years, does that mean it erupts roughly every 600,000 to 700,000 years, and therefore we're due? That idea often appears in magazines or television specials, but it's misleading. Volcanoes do not keep schedules. The intervals between eruptions are not exact, and the concept of being overdue is more a human invention than a geologic reality. Yellowstone might erupt again tomorrow, or it might slumber quietly for another million years. The past gives us context, not prediction. Still, the past does show us the range of what Yellowstone can do. From small lava flows to catastrophic super-eruptions, its history is one of extremes. And by studying that history, scientists can better understand what might happen in the future. If nothing else, it teaches us humility. We like to think of landscapes as stable, mountains as eternal, valleys as permanent. Yellowstone reminds us that the land itself can change in ways so massive that human history looks tiny in comparison. Think for a moment about those early humans who may have lived through the last eruption. They had no satellites, no observatories, no weather forecasts. They would have seen ash falling from the sky, rivers clogged, and animals dying, with no explanation beyond myth or fear. In some ways, we are lucky. We live in an age where we can measure, study, and prepare. But in another sense, the scale of Yellowstone's power humbles us just as much as it would have humbled them. So here's the question that lingers as we look back at Yellowstone's violent past. Does knowing this history make you feel safer because the last eruption was so long ago, or more uneasy because the evidence proves it can and does happen? If you could peel away the forests, rivers, and mountains of Yellowstone, lifting off the landscape like the lid of a box, what you'd see beneath would not resemble the tidy chambers of lava you might imagine from cartoons. Instead, you would see an enormous and complex system, a reservoir of molten and partially molten rock stretching for tens of miles, irregular in shape, like a sponge soaked in fire. It is less like a single pool of lava and more like a messy, layered network of heat, crystals, and gases spread across astonishing distances. Scientists have spent decades trying to map this system because what lies beneath is invisible to the naked eye. You cannot dig a tunnel and peer into the magma chamber. It is far too deep and too hot. Instead, geologists use seismic waves, the tiny ripples that earthquakes send through the earth, much like a doctor uses ultrasound or an X-ray. By measuring how those waves travel through different materials, they can build a picture of what lies below. What they've discovered is both humbling and unsettling. Yellowstone's magma system consists of at least 2 enormous reservoirs stacked beneath one another. The upper reservoir sits a few miles beneath the park. It is about 25 miles long, 15 miles wide, and a few miles thick. That alone is staggering. But below it, at a depth of perhaps 25 to 30 miles, lies an even larger reservoir, more than 4 times bigger than the upper one. Combined, they contain enough molten material to fuel multiple eruptions, though thankfully, most of that material is not fully liquid. In fact, Much of it is solid rock heated to a plastic, mushy state, like ice cream that's just beginning to melt around the edges. Only a small fraction, perhaps 10 to 30%, is molten. That ratio matters because it is one of the keys to whether magma can actually move upward to erupt. Think of the magma chambers as enormous pressure cookers. Inside them, molten rock is mixed with dissolved gases like carbon dioxide and water vapor. As long as that mixture stays under pressure, those gases remain trapped, like carbonation in a soda bottle. But if the pressure changes, if magma rises closer to the surface, for example, those gases can escape violently, expanding and pushing the magma upward in an unstoppable surge. This is why eruptions are often compared to shaking a soda bottle and then opening it. The release of pressure transforms a quiet container into an explosive spray. But the truth is that the magma system beneath Yellowstone is not constantly poised for explosion. For most of its long life, it simply sits, heating groundwater, feeding geysers, and producing small earthquakes. You could walk across the meadows above it, hearing nothing more than the wind in the grass, while beneath you lies enough molten material to alter the world. That contrast, the calm surface above and the restless heat below, is part of what makes Yellowstone so intriguing. Let's slow down here and talk about the role of water, because it is one of the overlooked but important parts of this system. Yellowstone is famous for its geysers, hot springs, and steaming vents. All of those features are powered by water seeping down into the ground, being heated by magma, and then rising back up. You can think of it as a massive plumbing system, constantly circulating. This hydrothermal network does two important things. First, it provides the park with its beauty, the colors of the hot springs, the eruptions of geysers, the hissing fumaroles. Second, it acts like a safety valve, releasing some of the heat and pressure from below. Without that constant venting of energy, Yellowstone might be more dangerous. In a strange way, every burst of Old Faithful is like a sigh of relief from the earth itself, a small release that prevents greater tension. Yet water can also create hazards. If groundwater becomes trapped and superheated, it can explode in what are called hydrothermal eruptions. These are not on the scale of a super eruption, but they can still be violent, blasting craters hundreds of feet wide. Scientists have found dozens of such craters scattered across Yellowstone, reminders that the park has a habit of suddenly coughing in ways that would be terrifying if you were standing nearby. Another key factor in the magma chambers is how they evolve over time. Magma doesn't just sit there like soup in a pot. It changes. New injections of molten rock from deeper in the mantle can recharge the system, adding heat, pressure, and gases. Sometimes, those injections are small, stirring things slightly but not enough to break the surface. Other times, they may be large enough to set off swarms of earthquakes, ground uplift, or changes in gas emissions. In other words, the magma system is not static. It is alive, in the slow and ponderous way that geology is alive. This leads to one of the more unnerving truths. Yellowstone doesn't need to be close to a super eruption in order to behave unpredictably. Even modest shifts in its magma plumbing can cause months of swarms, rising ground, or changes in geyser behavior. To scientists, those shifts are valuable data. To the average visitor, they might feel like background noise, easily ignored until they become impossible to overlook. It's important, though, to remember that the magma beneath Yellowstone is not unique in existing, it is unique in scale. Many volcanic systems around the world have magma chambers. The difference is that Yellowstone's is one of the largest ever studied. That size alone gives it the capacity for super eruptions. It's like comparing a campfire to a bonfire. Both burn, but one is capable of lighting up an entire valley. What fascinates researchers is that, despite decades of study, there are still enormous unknowns. How fast does magma move from the deeper chamber to the shallower one? How quickly can gases build up to dangerous levels? Could Yellowstone produce an eruption that is significant but not catastrophic? Something between a small lava flow and a full super eruption? These are not idle questions. They shape how we prepare, how we build monitoring systems, and how we teach the public to understand risk. To give you an idea of how much science has advanced, It was only in the last 2 decades that researchers even discovered the lower chamber beneath Yellowstone. Before then, models showed a single chamber, but seismic studies revealed a vast second reservoir below, dwarfing the first. That discovery changed how scientists think about Yellowstone's potential. It was a reminder that even when we believe we understand the Earth, the ground beneath us can surprise us with hidden complexity. And yet, the most striking thing about Yellowstone's magma chambers is how silent they remain most of the time. You can walk across the park, listening to the hiss of steam vents, the bubbling of mud pots, the calls of ravens overhead, and never suspect the enormity of what lies below. The danger is real, yes, but so is the quiet. Yellowstone is, for now, a sleeping giant whose breath is measured in geysers and whose heartbeat is counted in small tremors. So, here's something to ponder as you imagine these immense chambers beneath your feet. Do you feel comforted knowing that the system is mostly solid, unlikely to erupt in our lifetimes? Or does the sheer size of it, the knowledge that so much molten power lies under such calm landscapes, make you uneasy, as though you are living above a secret that is too vast to fully trust? If you ever visit Yellowstone, you will notice people staring at bison or marveling at geysers. What you might not notice are the quiet instruments scattered across the park, small boxes, antennas, and steel rods planted in the earth. These are part of one of the most carefully monitored volcanic systems in the world. Scientists watch Yellowstone as though it were a patient in an intensive care unit, with sensors acting like stethoscopes and thermometers. The patient is enormous, mostly quiet, and not expected to collapse anytime soon. But if anything begins to shift, they want to know immediately. The first line of monitoring comes from seismometers. These devices record the tiniest vibrations in the earth, picking up even small earthquakes that humans might not feel. At Yellowstone, earthquake swarms, clusters of dozens or even hundreds of small quakes are common. To most people, these would go unnoticed. But to volcanologists, the pattern, depth, and timing of these quakes are important clues. Earthquakes can mean magma is moving, water is shifting, or rocks are cracking under stress. Each quake is like a small cough, and when many happen together, scientists lean in to listen more carefully. Then there are GPS stations. These are not the GPS devices you use to navigate a road trip. These are precise scientific instruments that can measure ground movement down to millimeters. Imagine the ground beneath you, rising by the thickness of a fingernail. In a month, these sensors will detect it. Yellowstone's ground has indeed risen and fallen many times in recorded history. During the 1980s, parts of the park rose by more than 8 inches in just a few years, an enormous shift for a landscape. More recently, scientists have observed both uplift and subsidence, ground rising and then sinking again like the surface of a giant, slow-breathing creature. This breathing of the earth is one of the most watched signals, because it can suggest changes in the magma or hydrothermal system below. Gas emissions are another important clue. As magma rises or heats groundwater, it can release gases such as carbon dioxide or sulfur dioxide. Special instruments measure these gases at the surface, and changes in their volume or composition can be a sign of new activity. For example, a sudden increase in carbon dioxide could indicate that magma is closer to the surface, releasing its dissolved gases more easily. On a small scale, you can smell some of this yourself if you visit a sulfurous, rotten egg odor drifting near hot springs or vents. But the instruments track it with much greater precision, building a record over time. Another way scientists monitor Yellowstone is by watching its thermal features, the geysers, hot springs, and fumaroles. These features are like the visible skin of the system, reacting to changes below. If a geyser that was dormant for decades suddenly becomes active, or if the temperature of a hot spring spikes, those are signals that something in the underground plumbing has shifted. Yellowstone has more than 10,000 thermal features, and while no one can watch all of them, certain ones are carefully observed. Even satellite imagery helps, picking up subtle changes in surface heat from space. It may sound obsessive, but this constant monitoring is precisely what gives scientists confidence that a major eruption is unlikely without warning. If Yellowstone were preparing for something large, we would expect weeks, months, or even years of signals. Swarms of stronger earthquakes, significant ground deformation, sharp increases in gas output, and widespread changes in hydrothermal activity. In other words, the system would start shouting long before it erupted. Now, here's where the story becomes both comforting and slightly boring, which in this case is exactly what we want. In decades of modern monitoring, Yellowstone has never shown the kind of signals that would suggest a super eruption is on the horizon. Yes, the ground rises and falls. Yes, earthquake swarms occur, sometimes hundreds in a single week. Yes, geysers shift their patterns. But all of these are normal behavior for a restless volcanic system. They are the equivalent of Yellowstone stretching its arms, shifting in bed, or clearing its throat, not waking up to rage. To put this in perspective, consider other volcanoes around the world. Mount St. Helens in Washington, which erupted in 1980, showed clear warning signs in the weeks before earthquake swarms, visible bulging of the mountain, gas releases. More recently, eruptions in Iceland and Indonesia have been preceded by similar activity. Volcanologists have become adept at reading these signals. While no one can predict the exact hour of an eruption, the broader warnings are usually clear enough to give time for preparation and evacuation. If Yellowstone were to show such signs, it would almost certainly be detected. But here is a detail that may unsettle you slightly, even as it reassures you. The monitoring does not just protect against a super eruption, it also watches for smaller but still significant events. Yellowstone could easily produce a lava flow or hydrothermal explosion that might not threaten the entire world, but could cause serious local damage. Such events would also be preceded by signals, and the monitoring network is designed to catch those too. Behind all this data is the Yellowstone Volcano Observatory, a collaboration of agencies and scientists who gather, analyze, and publish updates. Their work is publicly available, meaning you can read monthly reports on Yellowstone seismicity, ground movement, and gas emissions. Most months, the updates are almost comically calm. Seismicity remains within background levels, or ground deformation is minor. If you are the kind of person who finds comfort in dull details, those reports are worth a glance. They are the scientific equivalent of a doctor saying, "Your patient is stable." Still, it is worth imagining what it would feel like if one of those reports suddenly changed. What if they announced that earthquakes were growing stronger, the ground was lifting several inches in weeks, and gas emissions were spiking? Even without an eruption, such news would ripple across the world. People living hundreds of miles away would wonder whether to leave. News outlets would descend on the park. The calm voice of the observatory would become the most closely watched set of updates on the planet. And here is where the human side comes in. Scientists can measure, record, and publish data, but they cannot erase uncertainty. The Earth is not a machine with perfect predictability. All of the instruments, all of the monitoring, all of the careful watching, these are ways of reducing uncertainty, not eliminating it. That is why volcanology is as much about communication as it is about measurement. Scientists must decide how to share their findings without causing unnecessary panic, while still being honest about the limits of their knowledge. In the end, the monitoring systems at Yellowstone are not just about science. They are about trust. You, sitting wherever you are tonight, listening as you drift towards sleep, are trusting that the people watching Yellowstone will see what needs to be seen and speak when they need to speak. And so far, they have done exactly that. But here is a question to carry with you. If the warning signs of a super eruption stretched out over months or years, how would the world respond? Would governments coordinate calmly, or would panic spread faster than ash? Would you pack your bags at the first hint of trouble, or would you wait for the official word that it was time to leave? Imagine you are standing in Yellowstone on a calm summer morning. Tourists are wandering between geysers, cameras ready, waiting for Old Faithful to spout its plume of steam. Families are eating sandwiches at picnic tables. Everything feels ordinary. And then, a small earthquake rattles the ground. At first, it feels like nothing unusual after all. Yellowstone has many small earthquakes every year, but within minutes, another comes, stronger this time. The ground shudders long enough that people stop walking and stare at each other, unsure whether to laugh nervously or to run. The first signs of a true eruption would not be cinematic explosions or fireballs. Instead, it would be a series of escalating tremors, each one stronger than the last. Glass bottles would clink together in backpacks. Car alarms might trigger. Birds would take flight from trees in sudden flocks. If you were standing in the park, you might see water in a hot spring slosh violently, as though stirred by a spoon. Then comes the first plume. In the case of a smaller eruption, it could be a dark column of steam and ash bursting from a new vent in the ground, accompanied by a roar like a jet engine. In the case of a super eruption, the beginning would be far more violent. The ground could split open along a fissure miles long, with magma and rock blasted high into the sky. The sound would be deafening, not like thunder, but like continuous rolling detonations so loud that your chest would vibrate with it. Ash would begin to fall almost immediately near the vent. At first, it might look like snow, grey flakes drifting gently downward, but within minutes, it would thicken into a choking storm. The ash would sting your eyes, coat your skin, and make it nearly impossible to breathe without covering your mouth and nose. Cars would clog the park roads as people tried to escape, their engines choking on ash. The sky, once blue, would dim to grey and then to an eerie twilight. For those not in the park but living in surrounding towns, the experience would vary. If you lived 50 miles away, you might first feel a distant vibration, a rattling picture frame on your wall, a window trembling in its frame. Then, after a delay, the sound would arrive, a low rumble, like a freight train passing endlessly by. Within an hour, ash would begin to drift down on your yard, your roof, your garden. Children might run outside to play in it, thinking it was unusual snow, until parents shouted for them to come inside. Further away, perhaps in cities like Salt Lake City or Denver, the first signal might be news alerts. Phones buzzing, radios interrupting their programming, television screens flashing, breaking news, Yellowstone eruption. At first, you might not believe it. The footage would look unreal, giant columns of smoke rising tens of thousands of feet into the sky, spreading outward like a mushroom cloud. Reporters would stumble over their words. Scientists would be hurried into studios, and everyone would be trying to answer the same impossible question: how bad is this going to be? The earliest physical effects would be ashfall. Ash is not soft like fireplace ash. It is sharp, gritty, and heavy, made of tiny shards of volcanic glass. When it lands, it clogs air filters, scratches lungs, and grinds into machinery. Within hours of an eruption, towns hundreds of miles away could be coated in inches of it. Imagine trying to drive through it. It would be like driving through a blizzard, but instead of melting snow, the particles would grind your windshield and clog your engine. Air travel would shut down almost immediately. Volcanic ash is deadly to aircraft engines, melting into glassy clumps inside turbines. The skies over North America would be emptied, planes diverted, airports shut down. For the first time in living memory, the continent's airspace would fall silent. And then there is the matter of the blast itself. In the worst-case scenario of a super eruption, pyroclastic flows, searing hot clouds of gas, ash, and rock would race outward from the eruption site at speeds faster than a car. They would destroy everything in their path within a radius of tens of miles. Forests, roads, and entire towns in Wyoming, Montana, and Idaho would vanish beneath a smothering, incandescent tide. Survival within that zone would be impossible. But outside that zone, millions of people would be dealing not with fire but with suffocating ash. Roofs would collapse under the weight of it. Rivers would clog, turning to slurries of mud. Crops would wither under the grey blanket deprived of sunlight. Even breathing would become a challenge. People without masks or filters would cough, choke, and struggle to draw clean air. The emotional reality of those first hours is difficult to overstate. You would be terrified, confused and disoriented. Imagine trying to call your loved ones as cell towers overloaded or failed. Imagine watching your city darken at noon, ash falling so thickly that you cannot see across the street. Imagine wondering whether to shelter in place or to attempt to drive somewhere safer, even as highways clog with panicked traffic. And yet, the experience would differ greatly depending on where you lived. Someone in New York might look out the window and see nothing unusual at all, at least for the first few days. They might scroll through footage on their phone, wondering if it was being exaggerated. Someone in California might notice a hazy sunset, more red than usual, without realizing that fine volcanic particles were already entering the upper atmosphere. The eruption would unfold in layers of immediate devastation near the caldera, choking ash across the continent and atmospheric effects that would circle the globe. Scientists have modeled these early hours in detail. They predict that an ash plume from Yellowstone could rise over 100,000 feet into the sky, far higher than commercial planes fly. Winds would then spread it in a vast fan-shaped pattern, determined by the season and the jet stream. Within days, states as far away as Missouri or Illinois could see inches of ash on the ground. Within weeks, fine particles could drift around the entire planet, beginning to affect weather and climate. But those early moments, the first quake, the first blast, the first blackening of the sky, would be the most shocking. They would mark the moment when Yellowstone changed from a tourist attraction into the center of a global crisis. And so, as you lie here tonight, perhaps comfortable in your bed, listening calmly, it is worth asking, if Yellowstone erupted tomorrow, where would you be when you first noticed? Would you feel the ground shake beneath your feet? Would you see ash falling on your car? Or would you be among those far away, learning about it through glowing screens, wondering if the danger would ever reach you? The first days after a Yellowstone eruption would be defined by the ash cloud. If the eruption plume rose high enough into the stratosphere, and in the case of a super eruption, it certainly would, the winds at that altitude would begin to carry volcanic particles across the continent with relentless efficiency. Unlike a thunderstorm, which blows over in an afternoon, an ash cloud spreads slowly, continuously, and inescapably. Imagine a grey veil stretched across the sky, reaching from horizon to horizon, and growing thicker every hour. For those within a few hundred miles of Yellowstone, the ash would accumulate in astonishing amounts. Some areas could see several feet of it in only a few days. Picture a town like Cody, Wyoming, or Bozeman, Montana. Streets buried, houses sagging under the sheer weight, and vehicles immobilized beneath layers of gritty powder. When wet, volcanic ash becomes heavy like cement. Roofs would cave in, barns would collapse, and power lines would snap. Farmers who had once relied on open fields would now see only a grey desert, where crops suffocated and livestock struggled to breathe. Further away, in cities like Denver or Salt Lake City, the ash would not be feet deep but still crippling. Imagine a few inches of ash covering every surface, the roads, the cars, the parks. It would be thick enough to shut down travel. Walking through it would feel like trudging through coarse sand. Breathing it would be hazardous without a mask or cloth. Even indoors, people would find fine grey dust creeping in through windows, coating tables, and settling into every corner of their homes. If you lived 1,000 miles away, in places like Chicago or Dallas, you might not believe at first how much impact this eruption could have on you. But soon, you would notice your car's engine struggling, its air filter choking with grit. Your city's water supply would grow murky as ash contaminated reservoirs. Grocery stores would empty, not only because local deliveries failed, but also because farmland across the heartland was blanketed in ash, ruining harvests. The ash cloud would be more than just a nuisance. It would transform the air itself. Sunlight would dim, filtered through a veil of suspended particles. The sky would no longer be blue but a sickly grey or orange, depending on the time of day. Temperatures would drop, not drastically at first, but noticeably cooler under the thickened sky. Some scientists estimate that within weeks, global temperatures could fall by several degrees. enough to shorten growing seasons and trigger widespread crop failures. Airports across the continent would remain closed indefinitely. Volcanic ash is not something you can simply sweep off a runway. It infiltrates jet engines and melts into glassy clumps, destroying turbines. Even military aircraft, designed for rugged use, would struggle in these conditions. The skies would grow unnervingly quiet, no contrails, no buzzing engines, just the sound of ash falling, like fine sand sprinkled endlessly from above. For ordinary people, life under the ash cloud would become a daily struggle. Every breath would be cautious. You would need to cover your face constantly, whether with a proper mask or a simple piece of fabric. Visibility would shrink to only a few yards when ashfall was heavy, turning a familiar street into a ghostly corridor. Roads would become impassable, not because of snow or rain, but because ash choked every surface. Consider a grocery store in Kansas City. Within hours of the ash starting to fall, people would rush to buy bottled water, canned food, and masks. Shelves would be stripped bare, not because trucks could not reach the city yet, but because everyone knew that they soon would not. A week later, ash would have contaminated the local river supply. Farmers' fields would be buried. Trucks would sit broken on the roadside, engines seized by grit. The once bustling city would fall into a muted quiet, its streets muffled by the weight of ash. And yet, the most disorienting part would be the darkness. Even at noon, the sky could resemble twilight. Streetlights might flicker on automatically in the middle of the day. Children would stare at the dim sky, asking why the sun looked so small and pale. Birds would vanish from the skies, many choking on the ash or fleeing in disarray. It would feel as if the world had shifted permanently into an endless overcast afternoon. Beyond the practical hardships, there would also be the psychological toll. Imagine lying in bed at night and hearing the constant patter of ash on your roof, like an endless drizzle of sand. Imagine waking in the morning to find your car completely buried. Imagine trying to check on neighbors, only to find the streets nearly impossible to walk through. Day after day, the grey powder would remind you that this was not a passing storm. This was a new reality. Historical eruptions give us a glimpse of what this might be like. When Mount Pinatubo erupted in the Philippines in 1991, ash traveled hundreds of miles, collapsing thousands of buildings and killing crops. But Yellowstone is on an entirely different scale. The amount of material released would dwarf Pinatubo many times over, spreading not just across a single region but across a continent. People in Europe, Asia, and Africa would soon see the effects too, not from thick ashfall, but from the haze in the atmosphere. Sunsets would glow brilliant red and purple. Temperatures would begin to drop globally. Farmers in distant countries would notice their harvests shrinking, not realizing at first that it was linked to the eruption half a world away. For you, sitting somewhere in the United States, the ash cloud would mean daily adjustments. Water filters would become essential. Cars would be abandoned. Outdoor work would be nearly impossible. Hospitals would fill with people suffering from respiratory distress, especially the elderly and very young. And even if you were safe indoors, you would feel the constant pressure of uncertainty. How long will this last? Scientists estimate that thick ashfall could linger for months. Winds would redistribute it, rainfall would compact it, and cleanup efforts would be slow and dangerous. The first weeks, however, would be the hardest, as the world adjusted to living under a shroud. So as you picture this scenario tonight, lying in your bed in peace, it is worth asking, if ash began to fall outside your window tomorrow, how would you respond? Would you shelter indoors and wait? Would you venture out with a mask, searching for supplies? Or would you look up at the darkened sky and wonder, with quiet dread, whether the worst was still yet to come? When people first think about a volcanic eruption, they imagine fire, ash, and destruction close to the source. But the longer-term consequences often come not from the blast itself, but from the way it dismantles the fragile systems that keep billions of people fed. Food is not just something you buy at the store. It is the end product of a chain so complex and delicate that even small disruptions ripple outward. A Yellowstone supereruption would not cause a small disruption. It would tear the entire chain apart. Start with the farmland in the western United States, some of the richest croplands on Earth. In places like Idaho, Montana, and Nebraska, fields of wheat, corn, and barley stretch to the horizon. These regions are often called the breadbasket of America. After an eruption, those same fields would be buried under layers of ash, ranging from a thin dusting to several feet deep. Crops would suffocate, roots would be poisoned, and irrigation ditches would clog with sludge. Even farmland not immediately buried would face devastation. The sky would be so dim that plants could not photosynthesize properly. Without sunlight, growth would slow, then stop. Now imagine you are a farmer in Kansas, far from Yellowstone but still under the drifting ash cloud. One morning, you walk into your cornfield, and instead of bright green stalks, you see grey dust coating every leaf. The plants look withered. Even if some survive the coating, the lack of light would kill them in weeks. And if you tried to save your harvest by washing the plants, you would find your irrigation water already contaminated. Tiny shards of volcanic glass in the ash would slice roots and leaves like razors, leaving nothing salvageable. Once farmland fails, the grocery stores fail. Supply chains depend on trucks, trains, and ships moving constantly. Ash would immobilize trucks by choking their engines, railways would clog, ports would close as ships avoided contaminated harbors. Even before international trade collapsed, panic buying would strip shelves bare. The average American grocery store stocks only a few days' worth of food. Without restocking, shelves would empty in less than a week. This is where the global ripple begins. The United States exports a massive share of the world's grain and meat. Countries in Asia, Africa, and Latin America rely heavily on these shipments to feed their populations. When the United States can no longer export, those nations face sudden shortages. Prices spike. People in wealthy countries complain about expensive bread and vegetables. People in poorer countries face starvation. We have seen smaller versions of this before. In 1973, a bad harvest in the Soviet Union led to global grain shortages. Prices rose so fast that entire governments struggled to stabilize their economies. During the eruption of Tambora in 1815, harvests failed across Europe and North America, leading to what was called the Year Without a Summer. Food prices quadrupled in some regions, and riots broke out. A Yellowstone eruption would combine both problems, magnified many times over. Think about dairy, meat, and eggs. Cows cannot graze on ash-covered fields. Chickens suffocate easily in dusty air. Pigs, often resilient, would still be unable to survive without clean water. Farmers would slaughter what they could in the short term, leading to a brief glut of meat. But soon after, the supply would vanish. You might find yourself in a supermarket where the meat section looks like it does before a holiday rush, except this time it never restocks. Fishing would not provide salvation either. Rivers across the continent would run grey with ash, clogging gills and killing fish. Reservoirs would become useless. Even ocean ecosystems could be affected as volcanic particles washed downstream, altering currents and poisoning coastal waters. For you, the listener, this might mean meals reduced to the simplest non-perishable goods. Canned beans, powdered milk, and bags of rice hoarded by those who thought ahead. Imagine boiling the same bland pot of food day after day, the flavors dulled by necessity. Coffee, chocolate, and spices, luxuries dependent on global trade, would vanish quickly. A morning cup of coffee could become something you only remember, not something you taste. The economy would follow the food. Modern economies are built on confidence that goods will move, businesses will stay open, and people can buy what they need. When that confidence breaks, markets collapse. The stock market would not merely dip, it could disintegrate. Investors would pull out of agriculture, transport, and manufacturing. Banks would fail as loans could not be repaid. Governments would scramble to provide aid, but how can you distribute food when the very roads are blocked by ash? Hyperinflation could emerge, not because money was worthless in itself, but because bread, rice, and clean water became priceless. Imagine walking into a store with a pocket full of cash and walking out empty-handed because the shelves are bare. Imagine farmers' markets reduced to a few desperate sellers trading moldy vegetables for gasoline or medicine. Globally, tensions would rise. Nations with reserves of grain might hoard them, cutting off exports. Others might attempt to take food by force. History shows this pattern clearly. During the Irish potato famine of the 1840s, hunger drove entire families to flee across the ocean. During World War I, blockades and shortages caused starvation, even in powerful nations. Multiply these crises by billions of people, and you can see how a Yellowstone eruption would reshape the entire planet. The social consequences at home would be just as sharp. Families accustomed to abundance would now ration their meals. Schools might close, not just because of ash, but because there was nothing to feed the children. Hospitals would face malnutrition on top of respiratory illness. Even prisons would struggle to provide food for inmates, leading to unrest. Perhaps the most sobering detail is how little it would take for food insecurity to spread. You might assume that living far from the ash cloud would spare you, but the food system is interconnected. If wheat cannot grow in Kansas, and corn cannot grow in Nebraska, and potatoes cannot grow in Idaho, then the shortage reaches your dinner plate, whether you live in Florida, Maine, or Alaska. The psychological impact of hunger is also worth noting. Humans can adapt to cold, darkness, even ash in the air. But hunger gnaws constantly. It drives desperation, anger, and conflict. Imagine whole neighborhoods where people whisper about hidden food supplies, where theft becomes common, and where trust dissolves. In such an environment, survival is not just about breathing through the ash, it is about finding enough to eat. And yet, even in this grim scenario, some would adapt. Communities might return to old methods of preservation, salting, smoking, fermenting. People might plant small indoor gardens with whatever light they could manage, using lamps or makeshift greenhouses. Trade would shift from dollars to tangible goods, food, fuel, medicine. Survival would become an act of creativity as much as endurance. So as you rest now, consider how fragile your food system really is. The apples in your kitchen, the bread on your table, the coffee in your cup, all of these traveled through vast networks to reach you. If those networks collapsed tomorrow, what would you do? Would you have enough to last a week, a month, or would you find yourself looking at a single can of beans, realizing that the world has changed in ways you never thought possible? When most people think of volcanoes, they think of lava glowing red, rivers of fire, and mountains split apart. But the real legacy of a super eruption is not the eruption itself, it is the sky. The ash and gases thrown into the atmosphere act like a veil drawn across the planet. They filter sunlight, dimming days into something that feels like twilight. This effect has a name: volcanic winter. The phrase might sound poetic, but the reality is profoundly cold, grey, and unforgiving. When Yellowstone erupts, billions of tons of sulfur dioxide would rise into the stratosphere, far above the clouds, where rain usually cleanses the air. Up there, sulfur dioxide combines with water to form tiny droplets of sulfuric acid. These droplets scatter sunlight back into space, cooling the earth below. It is like pulling down a set of blinds across the entire sky. Temperatures would not fall evenly. Some regions might cool by only a few degrees, others by more than 10. That may sound small, but even a few degrees drop can turn fertile farmland into barren ground. Think of how a late frost in your backyard garden can kill tender plants overnight. Now imagine that late frost stretched across continents for years. History gives us a preview. In the year 1815, Mount Tambora erupted in Indonesia, releasing far less material than Yellowstone would. The following year became known as the Year Without a Summer. In New England, snow fell in June. Crops withered in the fields. Families who had counted on harvests to last through winter instead faced hunger by autumn. Across Europe, the skies stayed gloomy, and food riots erupted in cities from Paris to London. That was Tambora. Yellowstone would dwarf it. Scientists estimate that global temperatures could fall by 5 to 10 degrees Celsius after a Yellowstone eruption. For context, during the last ice age, the Earth was only about 6 degrees colder than today. That difference was enough to cover North America with glaciers thousands of feet thick. Now picture such cooling happening not gradually over centuries, but suddenly, within months. You might think the cold would bring quiet beauty, like fresh snow after a storm, but volcanic winter is not the same as a natural winter. The light that filters through would be dim, scattered, and tinted. Days might feel like permanent dusk. Plants would struggle, animals would falter, and people would lose the rhythm of their lives without bright mornings and clear skies. Rainfall patterns would also change. Monsoons in Asia, which feed billions of people, rely on warm air rising from the land. Cooler land means weaker monsoons. The fields of rice that sustain families from India to China could dry up. In contrast, other areas might receive floods, as shifting winds carried moisture unpredictably. Imagine trying to plant crops in a climate where the rules no longer apply, where spring might never warm, and where summer might feel like November. The oceans would not escape either. Colder air temperatures would alter currents, which in turn shape weather worldwide. Fisheries, already stressed, might collapse. Coral reefs, sensitive to even small changes, could vanish. The chain reaction would spread from plankton, the foundation of marine food webs, all the way to whales. And then there is the psychological toll. Humans are deeply tied to the sun. We measure our days by its rising and setting. Without clear light, our bodies struggle. Circadian rhythms, the internal clocks that tell us when to sleep and wake, would falter. Imagine weeks where the sky never looks truly bright, where mornings blend into afternoons and afternoons into nights. Fatigue, depression, and anxiety would spread alongside hunger. But let's come back to you, sitting comfortably while listening. Picture waking up one morning in this new world. You look out your window and notice a dusting of grey powder on the ground. The air feels colder than it should for the season. You check the calendar, and it says July, but outside it feels like November. Your breath hangs in the air, and the trees look bare. What would you wear? How would you heat your home if power grids were already strained by ash? Even nations prepared for disasters would find their systems stretched thin. Energy grids rely on demand forecasts, predictions of how much power people will need. When temperatures plummet unpredictably, those forecasts collapse. Imagine cities in Texas or Florida, unaccustomed to freezing winters, suddenly facing ice storms. Power lines crack, water pipes burst, and people scramble for warmth. Volcanic winters would not just last a few months. Some estimates suggest the cooling could endure for a decade. Year after year, people would wait for the return of normal seasons, and year after year they would be disappointed. Farmers would replant fields only to watch them fail again. Children would grow up never knowing a true summer. Wars and migrations would likely follow. Throughout history, climate shifts have triggered human movement. The fall of the Mayan civilization, the collapse of Norse settlements in Greenland, even the upheavals of the Little Ice Age. All of these were tied to shifts in weather. A Yellowstone winter would be larger and harsher than all of those combined. It is worth remembering that humanity survived the Ice Age, but survival looked different then. Populations were sparse, and people were nomadic. Today, billions live in dense cities, dependent on infrastructure that assumes a stable climate. How would those cities fare if winters deepened and summers vanished? Would skyscrapers, built for air conditioning, endure prolonged freezes? Would underground transit systems flood when rainfall patterns shifted? Yet, perhaps in this darkness, there would also be sparks of adaptation. Human beings are stubbornly inventive. New greenhouse technologies, artificial lighting, and hydroponic farming might emerge as lifelines. Energy grids might pivot to nuclear or geothermal sources. Local communities might rediscover resilience through cooperation, sharing scarce food and heat. Still, the overwhelming question remains: how long could societies endure without the sun they depend on? And what would it mean for a generation to grow up under a dimmed sky, with the memory of bright summers becoming a story their grandparents told? When the ash has settled enough that you can see a few feet in front of you, the first thought is survival. Humans are remarkably adaptable, but adaptation requires knowledge, resources, and cooperation. In the immediate aftermath of a Yellowstone eruption, governments would face a dual crisis: protecting populations from ash and toxic gases, while simultaneously securing food, water, and energy. The challenge would be unlike anything in living memory. Imagine a city like Denver. Thick ash blankets the streets. Cars are immobilized. Airborne particles choke the air, making it nearly impossible to breathe without protective equipment. Hospitals fill quickly with people suffering from respiratory distress. Emergency services struggle to reach them. Firefighters cannot respond to every call because roads are blocked. Even basic communications are disrupted, as cell towers falter under the ash's weight or lose power. Governments would first activate emergency response plans, though few plans can fully anticipate a super eruption. Shelters would open, stocked with masks, water, and non-perishable food. Military units might assist with cleanup, distributing supplies, and clearing major roads. But the scale of the disaster would be overwhelming. Local resources would be quickly exhausted, and international aid would take time to mobilize. Communities would become the front line of survival. Neighborhood groups might organize to share supplies, distribute clean water, and monitor vulnerable populations like the elderly and young children. Skills long thought obsolete, such as growing food indoors, preserving supplies, and filtering water, would suddenly become essential. People might build makeshift greenhouses or use underground spaces to protect plants from ash and freezing temperatures. Food distribution would be the single most urgent challenge. Governments might attempt to ration supplies, but enforcement would be difficult in cities where panic sets in quickly. The black market for essential goods, water, canned food, fuel, would flourish. Imagine trying to barter a few cans of beans for heating fuel, or rationing a single loaf of bread among a family of 6. Resourcefulness and cooperation would be as valuable as currency. Energy would be another pressing concern. Power grids, designed for predictable weather patterns, would fail under ashfall and cold. Wind turbines might be clogged with ash. Solar panels, coated in grey dust, would produce little energy. People would turn to wood, coal, or other traditional heating methods, leading to further environmental stress. Communities might have to ration energy, creating schedules for heating, lighting, and water pumping. Water supply would also become precarious. Ash contaminates rivers, lakes, and reservoirs. Filtration systems struggle to remove fine particles, and contamination spreads disease. Collecting rainwater could be an emergency solution, but rainfall would carry ash, requiring additional filtration. People might boil water for safety, but fuel would be scarce. Every drop becomes precious. The psychological toll would be immense. Living under a dim, grey sky with ash covering everything creates a constant sense of oppression. Children might grow up never seeing a blue sky. Adults would struggle with depression, anxiety, and post-traumatic stress. Communities that can maintain social cohesion through communication, shared effort, and routines would survive better than those that fracture into fear and suspicion. Education and information would become crucial. Radio, satellite communications, and whatever functioning internet remains would serve as lifelines, keeping people informed about weather, food shipments, and safe zones. Governments would broadcast instructions for using protective gear, managing health crises, and locating clean water. Those who ignore warnings or lack access could face disaster quickly. Economically, societies would shift towards survival priorities. Manufacturing of non-essential goods would halt. Banking and finance would be disrupted as electronic systems fail or are overwhelmed. Local trade would revert to barter or alternative currencies based on essential commodities. Communities might become semi-autonomous, focused on self-sufficiency. As global trade collapses, healthcare would be stretched to its limits. Respiratory illness from ash inhalation, malnutrition from food shortages, and hypothermia from colder temperatures would dominate medical concerns. Hospitals would triage patients aggressively, and preventive care could fall by the wayside. In the most extreme cases, mortality could rise sharply until communities stabilize. Yet human ingenuity would not vanish. Underground shelters, once built for nuclear warfares, might be repurposed for ash-heavy regions. Indoor hydroponic farms could grow vegetables without sunlight. Schools might teach practical survival skills rather than standard curricula. Communities would rediscover old knowledge: how to preserve food, how to filter water, how to build heat-efficient structures. Skills once seen as archaic would become essential. Governments would also face hard decisions. Evacuation might be impossible in heavily ash-laden areas. Instead, strategies would focus on protecting populations in place, distributing respirators, cleaning streets, and providing heating and clean water. International coordination would be required to ensure food aid reaches countries dependent on US exports. Diplomacy and logistics would become survival tools as vital as guns or medicine. Despite the hardships, social bonds could strengthen in response to shared adversity. Communities that plan together, share knowledge, and pool resources would fare better. Individuals would learn to rely on neighbors rather than waiting for outside help. Survival becomes not just a physical challenge but a social experiment in cooperation, resilience, and ingenuity. But there would still be limits. Even the most adaptive societies would face trade-offs. Some regions might be abandoned if the ashfall is too thick or persistent. Populations might migrate south or east in search of more hospitable conditions, creating pressures on areas less affected by ash. Borders could become contentious as nations cope with sudden influxes of climate refugees. Technology would help, but only to a point. Satellites might provide updates on ash distribution and climate changes. Drones could survey inaccessible areas. But machines need power, fuel, and maintenance, all in short supply. Human labor, creativity, and adaptability would be just as critical as any advanced system. And yet, amidst all the challenges, some individuals and communities would thrive. Those who can innovate, cooperate, and maintain hope might rebuild faster, establishing networks of trade, local governance, and survival knowledge. Over time, human society would reorganize, prioritizing sustainability, self-sufficiency, and preparedness. So as you imagine this scenario from the comfort of your chair, consider this. If Yellowstone erupted tomorrow, how would you adapt? Would you rely on government aid or on your own skills and community? Could you survive weeks, months, even years under grey skies, with ash covering every surface and food scarce? How far would you be willing to go to protect your family, your neighbors, and yourself in a world suddenly turned hostile? In the aftermath of a Yellowstone eruption, the impact would extend far beyond ash-covered cities and struggling farms. It would shake global economics and politics in ways few could imagine. The world is interconnected, and when one of the largest volcanic systems on Earth disrupts the food supply, energy networks, and transport, every nation feels it. What might start as a local crisis in the United States would become a global upheaval. First, consider the immediate economic shock. North America produces a significant portion of the world's wheat, corn, and other staple crops. Within weeks of the eruption, production would drop sharply. Countries relying on imports from the US would suddenly face shortages. Prices for food, fuel, and essential goods would spike. Inflation would spiral. Stock markets, designed to respond to news and confidence, would experience unprecedented volatility. Investors would panic as the ash cloud interrupts transport, blocks ports, and cripples agriculture. Trade disruptions would be severe. Ocean shipping lanes might initially remain open, but as ash disperses across the continent, ports would close or become hazardous. Ships could not dock safely due to ash contamination, and engines could fail from fine volcanic dust. Air freight, critical for fast delivery of perishables, would be grounded for weeks or months. Even rail and trucking networks in North America would be paralyzed. The global supply chain, already finely tuned for efficiency, would collapse. Countries far from Yellowstone would feel these shocks almost immediately. Asia, Africa, and Latin America regions that import grain and meat would see skyrocketing food prices. In some countries, these price increases could trigger famine, riots, and political instability. Governments might respond with hoarding policies, cutting off exports to preserve local supplies. While this might help some populations, it would exacerbate shortages elsewhere, creating a cascade of crises across continents. Migrations would be inevitable. Millions of people in the U.S., particularly in the most affected western states, would be forced to move eastward or southward to escape the ash and find food. These migrations would place immense pressure on regions that were previously stable. Cities unprepared for sudden population influxes would struggle to provide housing, clean water, and medical care. Tensions between locals and migrants could escalate quickly. Internationally, migration pressures would rise as well. Countries dependent on North American exports might see desperate populations seeking refuge. Borders could become flashpoints for conflict. Nations might erect barriers, restrict movement, or deploy military forces to maintain order. At the same time, humanitarian organizations would be stretched thin, attempting to provide aid across increasingly hostile conditions. Political consequences would follow. Governments unable to protect their citizens from food and energy shortages could face widespread unrest or even collapse. Leadership crises might emerge in both developed and developing nations. Populist movements could gain traction, blaming foreigners, neighbors, or distant governments for shortages. Diplomatic relations could fray as nations compete for scarce resources. Global cooperation would be tested like never before. International bodies, such as the United Nations or the World Food Programme, would try to coordinate aid and prevent famine, but logistical challenges would be immense. Transporting food through ash-choked regions would take weeks or months. Cold weather from the volcanic winter would complicate delivery and storage. The question becomes not whether aid is needed, but whether it can reach the people who need it most. Energy networks would also face cascading failures. Ash and cold would strain power grids. Fuel production might decline due to logistical issues and supply chain disruptions. Countries dependent on imports of oil or gas could see prices soar. Those with domestic production would need to ration energy, creating social tension. Factories and refineries could shut down, halting production of essential goods and medical supplies. Financial systems, too, would be destabilized. Banks depend on functioning economies to maintain liquidity and confidence. In a world where food and energy shortages dominate daily life, financial transactions might falter. Hyperinflation could emerge in some regions, especially where governments print money to manage crises. Currency values could fluctuate wildly, destabilizing international trade further. Global markets would react unpredictably. Agricultural commodities would skyrocket, while luxury goods would collapse in value. Manufacturing might shift to essential items only. The result: worldwide economic contraction, potentially lasting years. Countries with strong reserves and diversified economies might weather the storm better, but even they would face social pressures as populations struggle to cope. Conflicts could arise directly from scarcity. Historical precedent shows that resource shortages often lead to war. During the Irish potato famine, tensions rose between landlords and tenants. In the Dust Bowl of the 1930s, migration and competition for farmland sparked local conflicts. Multiply these conditions globally, and it's easy to imagine border disputes, internal unrest, and even international skirmishes triggered by food and energy shortages. The geopolitical balance could shift. Nations with stable agriculture, energy independence, and strong governance would gain influence. Those heavily reliant on imports or with fragile political systems could falter. Alliances would be tested. Trade blocs might reorganize around survival priorities rather than economic efficiency. Countries once dominant in global trade could find themselves suddenly dependent on neighbors or rivals. Yet human societies are resourceful. Nations might collaborate to establish emergency supply corridors, using military logistics and humanitarian organizations to move essentials. Underground storage of food and fuel could become more common. Governments could introduce rationing systems, creating a new social order where access to necessities is strictly managed. Communities would organize to support each other locally, compensating for failures in larger systems. Still, the pressure would be relentless. Volcanic winter would persist, continuing to affect crops, energy production, and climate patterns globally. Populations would have to adjust to long-term scarcity. Migration patterns would reshape cities and rural areas. Social hierarchies could shift, favoring those who control resources, knowledge, or protective infrastructure. Those who cannot adapt would face dire consequences. Even distant nations would feel economic shocks through interconnected markets. For example, a country in Europe importing grain from the US might suddenly see its supply vanish. Commodity prices would rise, triggering inflation and social unrest. Governments would scramble to find alternative sources or negotiate aid, but supply chains disrupted by volcanic ash would make solutions slow and costly. And then there is the psychological effect on leadership. Decision makers would need to balance immediate survival with long-term planning, all while managing public fear and potential unrest. Choices about resource allocation, migration, and international cooperation could define the difference between stability and chaos. Poor decisions could exacerbate crises, while foresight and coordination could mitigate some of the worst outcomes. For individuals, the question becomes personal as well as global. Where would you go if your city became uninhabitable? How far would you travel for food, water, or safety? Would you cooperate with neighbors or compete for scarce resources? How much would your life change as society adapts to a new reality dominated by ash, cold, and scarcity? Ultimately, a Yellowstone eruption would demonstrate the fragility of modern civilization. Economies, supply chains, energy networks, and social structures are all built for a stable climate and uninterrupted trade. Remove those foundations, and the entire global system trembles. So, as you lie there listening tonight, consider this. If Yellowstone erupted tomorrow, how would the world respond? Would nations cooperate or compete? Would communities pull together or fracture under pressure? And in that new reality, what would your role be? Observer, survivor, or someone trying to rebuild amid chaos? In the immediate aftermath of the eruption, the landscape around Yellowstone would be unrecognizable. Forests flattened, rivers clogged, and ash blanketing every surface. But the changes wouldn't stop there. The environment itself would be transformed for years, even decades, shaping the way life could continue in ways most people rarely consider. Start with the soil. Volcanic ash is abrasive, acidic, and heavy. Where it accumulates in inches or feet, it crushes vegetation under its weight. The fine particles infiltrate the upper layers of the earth, altering its chemical composition. Minerals like silica, calcium, and magnesium may increase, which could eventually enrich the soil, but not immediately. At first, the ground would be sterile, unable to support the crops or forests that had once thrived. Imagine walking through a meadow only to find grey, glassy dust where grass should be. Roots would struggle to penetrate, water would not drain properly, and seeds would fail to sprout. Water systems would face similar challenges. Rivers and lakes near the caldera would become contaminated with ash and debris, turning once clear streams into grey, abrasive sludge. Drinking water would become unsafe without significant filtration. Groundwater could also be affected if ash infiltrated aquifers, meaning even wells that once provided clean water might now be hazardous. Communities would have to rely on stored water or trucking supplies from far away, creating logistical nightmares. Aquatic life would not fare well. Fish exposed to ash-laden rivers might suffocate or ingest toxic particles, disrupting the entire food chain. Frogs, insects, and other amphibians that depend on clean water would vanish from local ecosystems. Birds that feed on fish would struggle to find sustenance. The result would be a cascade of extinctions and migrations, altering the balance of the natural world. Forests would also take a hit. Trees might be knocked down by the force of the eruption, buried under ash, or weakened by prolonged exposure to dust and acid. In some areas, wildfires could ignite as dry ash and vegetation mix with lightning or human activity. Surviving trees would struggle to photosynthesize in a sky dimmed by ash and sulfur particles. New growth would be stunted, and the natural cycles of forest regeneration would be interrupted. Even plants and crops farther from the eruption would be affected. Ash drifting across the continent can coat leaves, reducing sunlight and clogging stomata, the tiny pores that allow plants to breathe and exchange gases. Photosynthesis slows or halts entirely. Crops like corn, wheat, and soybeans would fail to reach full maturity. Orchards could see fruit fall prematurely. Grasses for livestock would wither. In short, both natural and agricultural ecosystems would face near total disruption. Animals would respond in complex ways. Some would migrate to safer regions. Large mammals like deer, elk, and bears might travel hundreds of miles, abandoning traditional habitats. Smaller animals, less mobile, could perish in massive numbers. Predators that rely on those populations would face starvation, and scavengers might experience sudden booms in population before resources dwindle again. The ash would also introduce long-term chemical changes. Sulfur compounds in volcanic plumes can acidify rain. Acid rain accelerates soil degradation, corrodes infrastructure, and further harms plant life. Streams and rivers with high acidity can no longer support fish or amphibians, and entire ecosystems downstream from Yellowstone could shift dramatically over years. Erosion would become another issue. Once the ash settles, rain and wind would begin to move it across the landscape. In hilly or mountainous regions, ash-laden soil could slide downhill, creating mudflows or lahars that destroy whatever lies in their path. Roads, bridges, and towns could be swept away. Waterways filled with ash could overflow during storms, flooding agricultural valleys and towns, creating a secondary disaster atop the primary eruption. Wildlife would face a similar trial. Some species are adaptable and can survive in disturbed environments, but the scale and suddenness of Yellowstone's eruption would exceed normal recovery limits. Birds might relocate temporarily, but if food sources fail in new areas, they might starve. Insects could disappear in numbers, affecting pollination. Fish die-offs would ripple through aquatic ecosystems, and soil organisms that contribute to decomposition and nutrient cycling would be reduced, slowing the recovery of forests and grasslands. Air quality, long after the initial eruption, would remain poor in some regions. Fine ash can remain suspended for weeks or months, particularly if winds stir it back into the atmosphere. Even regions not directly beneath the eruption could experience hazy skies and respiratory risks. Long-term exposure could impact human health, agriculture, and natural ecosystems. Eventually, ecosystems would start to adapt. Pioneer species, plants and fungi capable of thriving in nutrient-poor, ash-laden soil would begin colonizing affected areas. Lichens, mosses, and hardy grasses could take root, breaking down the ash into more hospitable soil over decades. Insects would return gradually, followed by small mammals and birds, slowly reconstructing ecological networks. Recovery would be slow, but life has a remarkable capacity to rebound. Water contamination would persist, however. Ash in lakes and rivers could last for years, impacting drinking water and aquatic life. Cleanup would be difficult and costly. Reservoirs and dams might require dredging. Municipal water treatment plants would struggle to keep up, and rural communities without advanced filtration could suffer extended shortages. Even the oceans would feel indirect effects. Volcanic ash that settles into rivers eventually reaches the sea, altering salinity and chemistry along coastlines. Plankton, the base of marine food chains, could be affected, which in turn impacts fish populations, seabirds, and larger predators. The eruption would reverberate across ecosystems far beyond Yellowstone. Humans would need to adapt in tandem with these environmental changes. Farming practices would shift. Crop selection would favor resilient plants. Indoor or hydroponic farming might become common. Water filtration and storage would be essential. Communities might relocate closer to unaffected areas or create networks to distribute scarce resources. The natural world would be hostile, but with ingenuity, survival remains possible. Ultimately, the eruption would illustrate how deeply humans are intertwined with the environment. Ash might cover the land and disrupt life for years, but ecosystems would slowly heal. In the meantime, humans would have to navigate a world of scarcity, disrupted habitats, and environmental uncertainty. So, as you picture this, lying safely in your room, consider the landscape you know. Forests, rivers, farms, imagine them blanketed in grey dust, reshaped, temporarily destroyed, and struggling to recover. How would life adapt around you? How would humans and wildlife negotiate survival in a world so dramatically altered by a single geological event? After the immediate devastation, the ashfall, and the collapse of food systems, human society and the natural world would face years of recovery. The landscape around Yellowstone would remain unrecognizable for decades. Forests flattened, rivers clogged, and ash blanketing, everything would slowly give way to new growth. Ecosystems, though disrupted, have an incredible capacity to adapt. Lichens and mosses would be among the first to colonize the barren ash, breaking it down into fertile soil over time. Hardy grasses and shrubs would follow, attracting insects, small mammals, and eventually predators back into the area. Life, resilient and stubborn, would slowly reclaim what was lost. Humans, too, would adapt, innovate, and reorganize. In the immediate years after the eruption, communities would have relied on rationing, bartering, and cooperation to survive. Those lessons would become permanent, shaping a society more conscious of resources, self-sufficiency, and preparedness. Indoor farming methods, hydroponics, vertical gardens, and artificial lighting would likely become widespread, particularly in urban areas that lost surrounding farmland. Water filtration, energy conservation, and community planning would all be refined to withstand ongoing environmental challenges. The economy would stabilize gradually. Initially, trade routes had collapsed, industries had halted, and governments had scrambled to meet basic needs. But over time, logistics would be rebuilt. Crops would resume in areas less affected by ash, and nations would diversify their agricultural production to reduce reliance on a single region. Energy systems would be reinforced, incorporating a mix of renewables, nuclear, and localized power to ensure communities could survive localized disruptions. Financial systems would resume functioning once markets recalibrated to the new reality, though priorities would have shifted toward essentials rather than luxury goods. Migration patterns caused by the eruption would also reshape human geography. Some regions heavily affected by ash or climate changes might be permanently depopulated, while previously minor cities or towns could grow as people seek habitable zones. Infrastructure in these new population centers would be redesigned with resilience in mind: roads, water systems, and energy grids built to withstand ashfall, floods, or unexpected frost. Governments and communities would coordinate on a scale never before seen, recognizing that survival depends not just on individual preparation, but on collective planning. Food systems would become more robust. Crop selection would favor species resilient to shorter growing seasons and fluctuating temperatures. Storage and preservation methods would improve dramatically, reducing waste. Communities would adopt a balance between local self-sufficiency and global cooperation, understanding that while supply chains are fragile, human ingenuity can create alternative solutions. People might rediscover traditional knowledge: fermentation, salting, drying, seed preservation, and combine it with modern technology for maximum efficiency. Health systems, having been strained during the eruption and subsequent famine, would evolve as well. Hospitals and clinics would prioritize disaster preparedness, including air filtration, emergency nutrition supplies, and disease control. Preventive medicine and public health campaigns would focus on respiratory protection and long-term adaptation to ash-laden environments. Mental health would also be prioritized, as generations of people living under dim skies and facing scarcity would need support to prevent societal collapse. Education would change in response to the crisis. Children would learn not just reading, writing, and arithmetic, but survival skills, understanding ecosystems, agriculture, water management, and climate adaptation. Knowledge of local environments would be valued as much as global awareness, and curricula would integrate practical problem-solving with scientific understanding. Society, shaken by the eruption, would recognize that resilience depends on informed, capable citizens. Technology would play a vital role in recovery. Satellites could monitor ash distribution and climate shifts. Drones could map inaccessible areas, helping with reconstruction and agriculture. Energy-efficient lighting, indoor farming, and automated water systems would help communities survive and rebuild. Even as the natural world recovers slowly, human ingenuity would accelerate adaptation. Lessons learned during the crisis would shape new innovations designed to withstand future catastrophes. International cooperation, strained at first by shortages and migration, would become increasingly essential. Nations would establish contingency plans for global food distribution, energy sharing, and disaster relief. Policies and agreements created in the wake of Yellowstone would reflect a collective understanding. No country is entirely self-sufficient, and global survival depends on collaboration. Borders might be more permeable for humanitarian aid, and trade agreements would prioritize essential resources. Culturally, humanity would change. Art, literature, and stories would reflect the experience of living under volcanic winter, coping with scarcity, and witnessing nature's power. Generations born after the eruption would grow up with a profound respect for the planet's fragility and resilience. Communities would celebrate ingenuity and cooperation, and lessons from survival would become woven into societal values. Ecologically, Yellowstone itself would eventually recover. Forests would regrow, rivers would clear, and wildlife would return. Species that survived or migrated would recolonize the area. The eruption would leave permanent marks on the landscape, new calderas, lava flows, and altered river paths, but life would flourish in the spaces between these scars. Even as humans rebuilt civilization, nature would quietly reclaim its territory, reminding society of the balance between human activity and geological forces. Over decades, human settlements would find equilibrium with the altered environment. Crops would resume cycles, cities would function more efficiently, and communities would become more adaptive. While the eruption's memory would remain, it would also serve as a warning, guiding humanity toward resilience, foresight, and sustainable living. As you reflect on this from your safe, calm space, it's important to recognize the interplay of destruction and recovery. The Yellowstone super-eruption is a reminder of how fragile modern life can be and how resilient humans and ecosystems are in response. It shows the delicate threads that connect climate, food, society, and technology, and how quickly those threads can fray, but also how ingenuity and cooperation can repair them. So, as you consider this scenario, the question lingers: if humanity faced such a catastrophe, would we rebuild the world as it was, or would we construct something wiser, stronger, and more attuned to the planet? And more personally, how would you adapt, innovate, and survive in a world reshaped by fire, ash, cold, and years of challenge?